No problem. Yeah, hello. I will present you about the heat storage in abandoned mines, the research results from existing test facilities, and everything I will speak about is about the mine water thermal energy storage, so called MTES. And yeah, the basic concept of it is to use heat from above ground, put it into abandoned mines, into shafts, into galleries, and yeah, use heat conduction and bring the heat into the rock. But mostly you can't access all of the area in the abandoned mines, but this is an ideal case. If you have got go to a more realistic one, we have got some water flows, the heat convection due to the water flows via fractures or leakings is could be very high, and we are researching in this topic into projects. It's one in the coal area in Windsor, Florian told before, and in the ore mountains and the ore region in Freiberg with the Minatis project. And here we have got a picture from our Minatis basin inside our mine, the Reiche Zeche. It's a basin with 20 cubic meters of really harsh water with a pH of around 2. And the target of our project with colleagues from yeah, the Berg Academy Freiberg is to the establishment of continuous in situ monitoring in the mine to record effects of the geothermal storage, where we put heating and cooling into the water, including temperature sensors in the rock, so in the mine, directly in the water, and of course we sample the water, and we are sampling as well inside our test rig. So we provide as technical thermodynamics a mobile test rig, so a mobile mine water power plant that provides heating and cooling. So it's the heat sink and the heat source. And inside, we saw that before, we have got as well a plate heat exchanger with different plates, different coatings. And yeah, there we look about different cloggings, about defouling when we store heat or extract heat in different cycles, and the energy yield and purchase potential. So we are looking as well outside the box to consider the regional potential from yeah, maybe the city of Freiberg or other regions in our case, to look where are as well some storages. But inside our mine, we have got our basin with these 20 cubic meters, and beside the basin, there was drilled several boreholes with different temperature loggers from 80 centimeters to 2 meters in depth. You can see here the empty reservoir with the different borehole sensors and the rods, as well as in another picture, insulation cover when the reservoir is filled up with water. So we covered it so that we get less heat losses due to the air convection. And with our test rig, we use a mobile heat pump there to get heat in the reservoir, and where we get the heat from a second reservoir. And the heat pump has a heat power from around 4.2 kilowatt. And then in the next step, we add some more to get 12. Nowadays, it looks like that. Inside our mine, there are different logging systems inside the wall, in the water as well. We have got different logging systems inside our test rig with the tubes going into the basin. So this was the basin before. And with our test rig, I told you we have as well preheater to get like 12 kilowatt of heating power inside the basin to heat the whole basin up. And yeah, it works. the basin gets warmer. We see it here on the cover. It's a bit warmer than the water. The water is really red here. And the heat goes as well into the wall from the first and the third and all the cycles. And when we will look at our first cycle, we put 4,200 kilowatt hours of heat in our basin. So inside the water, there were stored 250 kilowatt hours. The most, of course, it's stored in the rock. It's about 2,800. But unfortunately, we get a loss via a flow. We didn't know that before, that we have got a water flow under our test rig, and we lost some water in the first test series. There we lost around 1,500 kilowatt hours, and of course we lost due to the cover around 150. But storage efficiency is roughly around 50%. And it worked. Heat storage works in our basin. And the current research status that we have got approximately 40 degrees Celsius inside the basin with these 12 kilowatt heating power. And by the mid of this year, we will do more research and more test cycles, as well as comparison the storage efficiency by 4.2 and 12 kilowatt hours. And here I've got a slide for you with all our cycles from now. And the bluish line is the water temperature. So the highest one is like 42 degrees Celsius inside the water. Then it goes to these yellow and reddish ones. These are the closest sensors in the wall. And from black to gray, we've got the furthest sensors in the wall. And when we will look maybe to the second cycle, where there's some zigzag there due to pump failure because of this harsh water, but with our test rig, with this 4.2 kilowatt hours of power, we reached 28 degrees Celsius. And then we've done an active cooling. So we restored or look like a winter time, and we used the warm water from our basin. And what was the reason? We want our baseline, these 11 degrees Celsius from the furthest sensors, to get back. And then we used more heating power to put it on the next level. And this was this active cooling. And now we will do a fourth cycle where we do active cooling from the high degrees. So our furthest sensors are roughly 18 degrees Celsius in 2 meters of depth. And then we will look about what will happen in the next couple of weeks. The second project is Windsor, as well with the colleagues from Fraunhofer in Bochum. And there we are using as well our small test rig. And this testing is especially for the optimization of the innovative heat exchanger system. So which operational management is the best maybe here for these EEG Kleinzeche in the real lab in Bochum. There we've done 2 test series and where we've developed some monitoring indicators. I will present you one later. As well, we've looked at the heat exchanger design and how we can use this for monitoring indicators. And additionally, we construct or thought about a conditioning procedure. So conditioning the water beforehand, before it reaches the heat exchanger, for example, by UV filtration. And what was more or less the outcome or the development? It was a testing from different test series where we include our test rig in Bochum. It's the first and second test series for the monitoring indicators. It's this bluish line and this reddish one. This zigzag and this reddish one is due to some pump tests in Bochum, some different pumping levels. That's why it goes like a bit, from down to above, and then. But our third and fourth test series in Freiberg, you can see here, this yellow and black one. This is for the testing of the conditioning module and a validation of these one. And yeah, we've developed these indicators, and the conclusion is, when should this heat exchanger be cleaned? So if there is maybe some clogging on the heat exchanger, can we predict this? And this was our target. Can we maybe still extract some heat, or should we clean it right now or in maybe a couple of weeks? That's why we have got like more like a traffic light system there from green to red. And if we've got from the heat flow comparing to the pressure loss, then we can estimate should our heat exchanger be cleaned. And this one is the test series from Bochum. The value depends from the volume flows. That's why it's in this green area. Other test series we've done nowadays, more or less last week. I've done this in our Reiche Zeche. Have got like a kind like of this area when we can say, okay, we have to clean it. And this works in different ones. We've tested it as well with other test series from us. And if you've got questions, please feel free and ask. And thank you for your interest and your attention.